A Cassandra node was OOM-killed every 6 hours. Heap was 4 GB, data size 500 GB. The assumption was a memory leak, but the real culprit was compaction falling behind due to a single-threaded strategy on a 32-core machine. Let's break down why compaction is the heartbeat of an LSM tree. Welcome to TheCodeForge. Before we dig into that production issue, let's cover LSM trees and SSTables. An LSM tree is a data structure that absorbs high write throughput by batching writes into an in-memory Memtable, then flushing them as immutable SSTables on disk. Background compaction merges these files to maintain read performance. This design eliminates random writes, making it ideal for write-heavy workloads. Every write first goes to the Memtable, an in-memory sorted structure like a skip list. This is fast with no disk I/O. When the Memtable reaches a size threshold, it's frozen and a new one takes over. The frozen Memtable is flushed to disk as an SSTable in a sequential write, which is fast even on spinning disks. Here's a simplified Memtable flush logic similar to RocksDB. The put method inserts into a skip list and tracks size. When the size exceeds the threshold, it triggers a flush. The flush thread writes the sorted data to an SSTable as a sequential write. Reads are the Achilles heel of LSM trees. Without optimization, you'd have to search the Memtable and every SSTable. Bloom filters tell you if a key is definitely not in an SSTable, avoiding disk reads. An index allows binary search within an SSTable. In practice, a point lookup touches only 1-2 SSTables. This code shows how an SSTable handles a read. First, it checks the Bloom filter. If the filter says the key might be present, it looks up the offset in the index and reads the data block. If the Bloom filter says no, it returns null immediately, saving a disk read. Compaction merges multiple SSTables into one, removing overwritten and deleted keys. Size-tiered compaction merges files of similar size, while leveled compaction organizes SSTables into levels with exponentially increasing size. Leveled is better for reads, but causes higher write amplification. Here's a simplified leveled compaction logic. Each level has a target size, growing by a multiplier, usually 10. When a level exceeds its target, a file is picked and merged with overlapping files in the next level. This keeps the number of SSTables per level bounded. LSM trees aren't a silver bullet. For read-heavy workloads with large range scans, B-trees are faster because data is stored contiguously. If you need strict ACID transactions, a B-tree with MVCC like Postgres is simpler. If your data fits in memory, an LSM tree adds unnecessary complexity. This is the same issue we highlighted at the start. Here's exactly why that happened. Compaction was falling behind because a single-threaded compaction strategy couldn't keep up on a 32-core machine. Pending compactions grew, causing Memtable flushes to pile up. Each flush consumed memory for new SSTable writers, and the OS page cache ballooned, eventually OOM-killing the node. The fix was to switch from size-tiered compaction strategy to leveled compaction strategy and set concurrent compactors to 4. Additionally, increasing Memtable heap space in MB to 2048 reduced flush frequency. Compaction caught up, memory usage stabilized, and the OOM kills stopped. Leveled compaction can cause 10-30x write amplification, meaning each byte written is rewritten multiple times. For write-heavy workloads, this can wear out SSDs quickly and reduce throughput. Consider size-tiered compaction for write-heavy scenarios. A single-threaded compaction strategy on a multi-core machine can cause compaction to fall behind. This leads to unbounded pending compactions, memory pressure, and eventually OOM kills. Always set concurrent compactors to at least the number of CPU cores. A common mistake is setting Bloom filter bits per key too high. With 40 bits per key and 1 billion keys, that's 5 GB per SSTable. If you have many SSTables, memory usage can balloon. Use 10 bits for -1% false positive rate or 20 for -0.02%. The article mentions format version equals 5 for partitioned Bloom filters. This option is available in RocksDB 5.15 plus 2018. In older versions, Bloom filters are monolithic, causing higher memory overhead. Always check your RocksDB version before enabling this feature. The article discusses write stalls but doesn't show how to configure them. Here's a RocksDB example setting stall triggers to prevent OOM, max write buffer number limits pending memtables, and delayed write rate throttles writes when compaction lags. The article mentions tombstones but glosses over a critical production issue. In Cassandra, frequent deletes can cause tombstone scans that spike read latency. Monitor tombstone scanned histogram and consider using TTLs instead of explicit deletes for time series data to avoid this. To diagnose issues, start by checking write stall metrics and pending compaction bytes. Monitor bloom filter effectiveness with RocksDB bloom filter full positive. If compaction is falling behind, increase max background compactions or run a manual compaction. Let's run through some common interview questions. How does an LSM tree handle concurrent writes? Writes go to thread local Memtable or concurrent skip list. Reads check Memtable lock-free, then SSTables. When choose leveled over size-tiered, leveled for read-heavy, fewer SSTables, size-tiered for write-heavy, lower write amp. What happens when compaction can't keep up? Memtable flushes pile up, L0 file count grows, red latency spikes, write stalls occur. And a few frequently asked questions. How do LSM trees differ from B trees? LSM optimizes writes via sequential appends, B tree optimizes reads with in-place updates. How to reduce write amplification? Use size-tiered compaction, increase level multiplier, or reduce number of levels. What are tombstones and how to manage them? Tombstones mark deleted keys. They accumulate if compaction is infrequent. Increase compaction frequency or trigger manual compaction. To recap, LSM trees turn random writes into sequential appends, making them ideal for write-heavy workloads. Bloom filters are crucial for read performance. Compaction is the heartbeat of an LSM tree. If it falls behind, the system stalls. And remember, LSM trees aren't suitable for all workloads. Ready to go deeper? Up next, distributed consensus. Paxos and Raft, then leader election, then quorum, R plus W, N. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.